I hope that made your dog bark at your house if you have one. Or I hope that made your cat run off in a different room, because if so, I strike again. I win. All right, so in the last video, we talked about zinc and extracting zinc from pet food and how we can run this on atomic absorption. And in this video, we're going to talk about the spreadsheet, because the spreadsheet's going to have calculations, and you're like, oh no, math, I hate math. Well, okay, it's not going to be as bad as what you think it is. It's just a weird unit that a lot of people have or are uncomfortable with when they see it and they have to use it. But I promise you, it's no different than what we've been doing all up until this point. So what you're seeing here on the screen is an example of an Excel spreadsheet template. Your format might look slightly different. I could have rearranged data. I could have added just a few things, or taken away a few things, or shifted something from one spot to the next. But all the basic information will still be here. And up here at the very top, this is going to be your section that you are going to draw, please. I'm the one that's drawing, that you are going to key in as far as lab data goes. So the wavelength that you chose, the slit width that you chose, the voltage that says milliamp that you ran, and then here's the term linearity. It's linear up until a certain point, but if you're using, I would say, newer instrumentation, what you will find is a check standard that will give you a 0.2 absorbance. So it gives you kind of the minimal, not the maximal, I guess. But you can find linearity in a standard kind of AA manual. So very often these metals will have a linear range where the beginning and the end window is suitable for the AA instrument as far as standards go. So you'll be able to find that. We've got one of those reference books in the lab. We'll show you where it's at if you ask for it. And you can just find zinc, and zinc will have it stamped on there. Here is the linearity, and you just go from there. So let's talk about the calculations. First off is part A, and part A is all about the standard prep. So here are volumes that the person used in order to make the standards with. These are the volumes that the volumetric flask was diluted to. So everything was made in 100 mils. You probably did the same thing as well. And then here were the concentrations that that person ended up with. So simply it's CV equals CV, and you get Excel to do the calculation for you, and that calculates the ppm. Keep in mind these color-coded blocks, depending on what colors that they are, there's a nice little piece up here at the top that will identify those. You do not want to key these numbers in. You want Excel to calculate them for you. So very important that you get Excel to do the majority of the calculation work embedded in a spreadsheet. So what we've done is that this person ran some standards, got some absorbances, and then those absorbances, of course, were entered here in the Excel spreadsheet as well. So nothing surprising. I mean, this is kind of the run-of-the-mill calibration type of work that we have become very, very familiar with up until this point. So what will happen is, let's say I delete this graph. I'll go through the motions of adding the graph in just so you can see that again. So this person is going to start with the 0, which is blank, because that really is a standard. That should be something that is plotted in a calibration curve. So we're going to click and we're going to drag down, and that will highlight all of the standard part per million concentrations that you made in the lab. And then you just kind of drag it over as well, and that highlights all of the absorbance values that those standards came with once they were ran and analyzed on the machine. All right, so I'm going to highlight those two columns, and then up here at the top, I'm going to go to Insert. And when we do, there's a middle section, and I'll see this word called Charts, and that's what I want to insert. So right up above is an example of a scatter plot. We just want points only. That is it. So I'll click the drop-down arrow, and it gives me a few options. There's the spots only, the data points. A version where curvy lines connect everything. Another version where it's just curvy lines and no points. And then another version where it's straight lines that connect everything. And then straight lines with no points. So like usual, we always go to scatter plot. and this is what we get. So it looks like this is pretty linear, right? I mean, at face value, my eyeballs are like, all of those kind of line up pretty well. That's great. That's what they should be doing. And even on Excel, they should be doing, it should be close to linear. Now, keep in mind, the AA instrument uses new rational, so it accounts for slight curvatures in a way. But on Excel side, when we manually do these, we use Excel. All right, so I'm going to click up data point, and like always, right-click on one of the data points when they're highlighted, and then go to Add Trend Line. And a pop-up box will show up here to the right-hand side. We're going to choose linear. And then down toward the bottom, we display the equation and we display the r-squared value. All right, so I'm going to close that box out just by hitting X. And there's my information that I will need to plug in to that box and that box. So it looks like it's 0.5573. So I've keyed that number in manually already. And this is a negative 0.0029. Now, my template that I always provide you is always X plus something, because more so than not, it is X plus something, and that's what we see most. But in this case, there is a negative. It's not a positive. So I've got to keep that negative in place, and I do that by just keeping it with the value here. So that is a negative 0.0029 that gets keyed into that block based on the absorbances that this person generated using their standards. So your regression line will be slightly different, but still it's there. All right. Okay, so there's section A. I don't think there's any surprises here that go along with the sample analysis or the standard analysis. I will also say, though, this AA machine, that will also give you a regression line. And that regression line will be different for the AA. These two will not match. And that's fine. They'll be close. Your answers that it has generated and the answers that you've generated, they will be really close together, but they will not be exact matches. So I just want you to keep that in mind as you go further into the sample analysis of why things aren't perfectly aligning up on your side. And that's not a big problem. That's just the difference in the regression line types that we are using versus the instrument. But it's also why we prefer the number on the instrument better. Okay. All right. So next it says, note, if the AA instrument generated a calibration curve, use those ppm values on the report. However, you will still need to plot the calibration curve manually on the spreadsheet. So this is just going through the motions of plotting a cal curve. That's what we're doing here for part A. I know the instrument did it. I know the instrument did it. But we still want you to understand where that information is coming from, and we never want to lose that. So yet again, we plot another calibration curve. All right, next up is section B. And section B now focuses all on the samples, and you're seeing 3 samples that are here. I just made these numbers up in a way. So 0.1 grams is kind of your target based on the previous lab video, based on the lab directions that we were provided. It looks like this person used 0.2 instead. Whatever, it doesn't matter. I'm just going to go through the motions of using this example problem here so you've got something to go by, and that way you can apply the technique to your samples only. So first off, the absorbance of the food sample, so 0.27008. So 0.2788 is going to be the absorbance from that food sample that was processed by this person. Yours will be different, but it's there. This is absorbance, so that is our Y variable, because if I go back up here to the top in our calibration curve, I'm going to see that that 0.2788 is absorbance, and absorbance is plotted on the Y-axis. So 0.2788 equals 0.5573, and then we're going to subtract 0.0029 from that number. So it's really just a little bit of algebra at this point. I'm going to take 0.2788. So I'm going to minimize this so you can see this all at the same time. So we're going to take 0.2788. We need to get X by itself, right? It's 2788. So we got to get rid of, sorry, that's 0.5573X. So forgot the most important thing. So 0.2788, and then we are going to get rid of everything around x first. So we got to get rid of that negative 0.0029. The opposite of subtraction is addition, so I'm going to add 0.0029 onto that number, and I get 0.2817. So this is 0.5573 times x, so the opposite of multiplication is division. So I'm going to divide by 0.5573, and then I hit equal. So the number that I should get here is 0.50547, which rounds to 0.5055, and that's basically what you're seeing below the 0.2788 absorbance on your screen. That's how that number was generated. But if you notice, this is a calculation. Get Excel to do the calculations for you. So you're going to hit equal. So I'm going to just delete that, right? So I'm going to hit equal, and then I'm going to open the parentheses up, and I'm going to say, hey, we need 0.2788. And it looks like I am going to normally, if this is a regression line, x plus a negative number, I'm going to do the opposite of addition, which is subtraction. And then I'm going to click that negative number. Two wrongs make a right. So if I'm subtracting a negative, I'm actually adding it. And that's exactly what we need to do here. So I'll close that parentheses up, and then I'm going to divide by 0.5573. So I'm going to click that value on the Excel spreadsheet, and then I'm going to hit enter. And that gives me the exact same thing that we did by hand, 0.5055. I'm not going to worry about the other two columns because they're all treated in the same way. We're going to go through this calculation one time as an example. Next up is the mass of the food sample. So the mass of the food sample is 0.1. So this person used 0.1 just like you used 0.1. Again, their absorbances was 0.2788, but yours is going to be different. Yours might not be 0.2788. Yours might be greater. Yours might be lower. Yours might be kind of close. It really just depends on the food sample that we brought in, because depending on year to year to year to year, it's all different food samples that will all carry different amounts of zinc maybe. So that number will definitely change. 0.1 though is pretty standard for us. I mean, again, if the lab directions tell you 0.15 or a 0.5 or a 0.2, then go with that. But this 0.1 is kind of where we're at. So 0.1 grams of solid food sample that we weighed out. And from gram to milligram, we did a conversion. Notice these are also pinkish or peaches. So we want Excel to do those calculations as well. So from going to gram to milligram, we guess what? Multiply by 1,000, right? So 0.1 times 1,000 is 100. So just like before, I can go in and hit equal, and then I'm going to click this number, 0.1, and then I'm going to multiply it by 1,000 and then hit enter, and that gives me the mass of the food sample in terms of milligram. Next up is the mass of food sample in kilogram. All right, well, the reason for this is because eventually we're going to have to report our numbers based on milligram per kilogram amount, and I need the kilogram here in order to do this. So get Excel to do this as well, and you got to keep in mind, kilogram is a unit that we don't see or that we don't work with too often, right? It seems like it at least. So there are 1,000 grams in 1 kilogram. So kilo is 1,000. It's just a bigger unit, right? It takes 1,000 individual gram units, and that grouping is a kilo or a kilogram. So that 1,000 gram equals a kilogram. So if I do this by hand, I would be doing 0.1000 grams over 1. And then in the next step, gram on top, gram on the bottom, and I need to go to kilogram. Well, 1,000 is with the gram, so 1,000 is with the gram, and that's equivalent to 1 kilogram, and 1 kilogram goes there. So it looks like I'm going to take 0.1, and I'm going to divide by 1,000 here. So I can hit equal, and I'm going to click on 0.1, and I'm going to divide by 1,000, and I hit enter, and that gives me the same value, but this time in terms of kilogram. So I'm not going to use this right off. I will use it later on, but we need it in here, and this makes the most logical sense of where to put it. So that way, when we get to that point, it's ready to go. We did that calculation, and we can use it. All right. Next up is the volume used for the preparation. So that volume was 100 milliliters. This was the sample size, right? That's what this was. So I took my 0.1, I digested it on a hot plate in an oven, I added nitric, I filtered it, blah, blah, blah. But I filtered it into a 100 ml volumetric flask. Again, that's what this person did. If it is not 100 mils when you did it, then you need to use whatever appropriate volume that was. Is it a 50 mil flask? Is it a 250 mil flask? How did the sample prep go? So keep that in mind. Don't make the mistake and just copy and paste over everything that you're seeing in the video. I am only going through an example calculation. That's what I do with these videos. That's always what they've been about. So you can apply your own data and your own prep and know kind of what to handle or what to do with it. So that is mil. And in the next step, it says, okay, well, this is the volume used for the preparation, but this time in terms of liter. I know it doesn't say in liter, beside of that, it chopped it off, but that's what that number is. So we need this into liter. We talked about that already in the lab prep video when we talked about the procedure. So just as before, there are 1,000 milliliters in 1 liter. So if I used 100 milliliters over 1 milliliter on top, milliliter on the bottom, I go to liter. So there are 1,000 with the mils, so 1,000 goes there. There's a 1 with the liter, so a 1 goes there. So I'm going to take 100 and I'm going to divide by 1,000. Keep in mind, ones don't matter. 100 divided by 1, 100. Times that by 1, same number. Divide it by 1,000. That's really the only applicable thing that goes on. So with this one, I'm going to hit equal, and I'm going to click on 100, and then I'm going to divide by 1,000 in order to give me a liter for that value. So 0.1, there we go. I know you could do that in your head, but it's always good to get Excel to do these calculations. So that way you've got a template. And if you did not use 100 but 50, you can key that number in, and then all of a sudden the number begins to update. Or, hey, we did 25 mils. I key in 25, the number updates because that number is used in other calculations down the board. So we used 100 mils in this example. Next up is the actual number of milligrams in the sample. So how on earth are we getting that value? This is probably where you're going to get your first little monkey wrench that begins to happen and figuring out how to handle this. Not a big deal. Keep in mind, these units are part per million. And part per million basically means milligram per liter. So if I go back up to this ppm value of zinc, and this ppm value of zinc is 0.5055. That means 0.5055 per 1 liter, right? So what we want to do is that we want to calculate how many milligrams of zinc was not in a liter. We didn't prep a liter. We prepped 100 mils. I don't want concentrations. I want the actual amount. I want the actual number of milligrams of zinc from that food sample. That is what I'm after. So if this concentration, milligram per liter, is giving me an idea of that, then what I can do is I'm like, okay, well, how many milligrams were contained in the 100 milliliters of the sample that I prepped? Because that's what we prepped in this example. We didn't make a whole liter of a solution that we then ran. We made 100 mils of a solution that we ran. I'm trying to calculate the actual milligram amount in that 100 mils. That is what I'm after. So it's not necessarily concentration. It is like a legit amount that is present there. Okay. So here's the story with this. there's a little bit of a problem because this is 100 mils and that is 1 liter. So I need to convert 100 mils into a liter, and I take 100 and I divide by 0.1, right? Or divide by 1,000 and I get a 0.1. So we did that already. That's right up here at the top. I spelt volume wrong, but I'll try to fix it by the time you get it. But it's right there, 0.1 liter. So in order to solve for this algebra problem, right, this is trying to give me the actual number of legit milligrams in the zinc sample that I prepped. We need to cross multiply and divide. So what that means is that I'm going to take 0.5055 and then I multiply by 0.1. There we go. So 0.5055 and we multiply by 0.100. And then that is equal to, this is 1 times x, right? And I'm going to do that in a different color, so that way you know kind of what stays together. This is just a ratio and proportion problem. That's all that this is. So I'm going to take 1 times x, and 1 times x is, of course, just x. So this looks like really the only thing I have to do is take 0.5055 and I multiply by 0.1. And that will tell me the number of milligrams of zinc that is inside of that 100 ml volumetric flask. So that's what you're seeing here. I can hit equal. And then what happens is that I click on the concentration of 0.5055. And I don't need that. So let me drag that over. It's going to get confused here. I've got too much going on. All right. So, and you probably feel that way too in the class. All right. So I'm going to hit equal, and then I'm going to do 0.5055. And then I'm going to multiply by 0.1 because that is the volume in terms of liter that we prepped. So again, very important that I keep Excel doing the calculations. Do not manually type these in. And then I'll hit enter, and that gives me 0.05055. Okay, so that is the actual number of milligrams of zinc inside of that 100 ml volumetric flask. Next up, what is the concentration of zinc now in terms of milligram per kilogram? And this is milligram per kilogram, kilogram meaning from your sample size. So the way that we process that type of calculation, not a big deal. So the number of milligrams that I just calculated was 0.05055 milligrams of zinc, right? We just did that calculation. It's now in Excel. It is ready to go. So that number we're going to have to use. And then we're going to divide this because this means milligram per kilogram. So we're going to divide it by the kilogram of sample, right? That's what we're after. So if I weighed out a kilogram or 1,000 grams, if I weighed out 1,000 grams of that pet food sample on a balance, how many milligrams of zinc would be contained in that 1,000 gram sample, right? That's kind of what this concentration is trying to tell me, but it's based on kilogram amount because that kilogram amount is from our sample size. We processed the sample. We did not process 1,000 grams. We did 0.1 gram. So based on all of the information that's out there, I need to know how much zinc is contained in a kilogram of pet food. That is what this concentration is trying to do. So no big sweat, right? We already did that calculation. That calculation's right up here at the top. So it looks like we did a mass of a food sample, and that mass of the food sample we did in kilogram. And I told you just a few minutes ago, we're going to need that number for something. And now's where we use it. So I'm going to divide that by 0.0001. That's what this number is going to be divided by, 0.0001. Your number might be different because maybe you did not measure out 0.100000 grams. You go by your mass because the amount of zinc that you're going to be extracting is based on your mass. If you weighed out more, you're going to get more zinc. If you weighed out less, you're going to get less zinc. But this is a concentration that is based on per kilogram amount. So it corrects for all of those little slight mistakes that might happen in a lab. It's no big deal. So if we did have a kilogram, if we did measure out that much, if we did digest that much, and nobody would want to, it's a waste. But if we did, how many milligrams of zinc would show up? So when you do that in Excel, what will happen is that you will come here, you'll hit enter, and it looks like I need to click my 0.05055, my actual number of milligrams in the sample that I used, divided by the amount of sample that I used in terms of kilogram. And then I hit enter. And I get a big whopper of a number, and it says 505 milligrams per kilogram, right? That's what this is, 505 milligrams per kilogram. So if I go back to this background section, I got 505. Does it fit within the recommended window that the American Association of Feed Control Officials have set out? And it looks like the window here is 120, so it's greater than 120, all the way up to 1,000. So I can go all the way up to 1,000 here and be okay. They're fine with that. And my number is 505. It's almost kind of in the middle, not quite, but kind of in the middle. So yeah, it looks like this pet food sample does fit that criteria that they recommend. Now, the other part of this is you're going to see a question, and it's going to say, okay, well, guess what? Now we are going to have to do this. And when we do it, we want to know, does it fit the bag information? So there is sometimes bag nutrition labels that happen on the backs. And most of the time, we are not going to provide you this in the beginning. So this is a number that we will share after the fact, if we can find one. There's a chance that we won't be able to find it. But if we can find one, and if you did process one of those samples, we will share that out with the class, and you'll know what they're stating is inside of their pet food. So we're going to see, does it meet that window, right? Are we really close to that accepted value? Yes or no? So here what's happening is that is where the theory percent comes from. That 250 milligram per kilogram for this particular brand of food, that is what was stamped on the bag label. Or we went to their website and we found it there. And they're saying 250 milligrams per kilogram. That's what we've got. But based on our analysis that this person did, this is almost double. Right? It's not 250. It's almost double that. It's 500. So don't be alarmed. You're giving your pet double the amount of zinc that's on the label, but that's okay because you can go all the way up to 1,000 according to the regulatory body and be fine with that. It's just the label is not an accurate claim of what's inside of the food sample based on our lab studies. Also, keep in mind that some of the bag labels will use the word minimum, right? They do not want to be involved in any type of lawsuit. So they will say a minimum of 120. And that way, if their food does come back at a 500, then they're going to be like, oh, well, we only told you it was a minimum of 120. We're meeting our minimum of 120. But it could be anything else above that. And it just so happens that when we process this batch, based on what we did in our manufacturing, it just came out to be a little bit more. And just use that as a little bonus. You got extra zinc for your pet because you don't want them to have a zinc deficiency, do you? Well, as you can imagine, that works up until a certain point. But after a certain point, you start to venture into the maximum areas of what they recommend your pet to have, or a person. If this was some type of nutritional supplement, such as a multivitamin or some type of multivitamin drink, if it's not a tablet or a gummy. I mean, these things, they have very large windows for a reason. And that's so you don't sue the bejesus out of them if you find that these things begin to happen. All right. So once you do that with your 3 samples, in this particular scenario, these 3 samples came from the same brand. And because they came from the same brand, we can calculate an average and we can calculate a standard deviation. If your samples did not come from the same brand, you cannot calculate the average and the standard deviation. You just can't do that because they're different samples from different manufacturers, from different supplies, from different batches. It's not going to work for you. So if you're using samples from 3 different brands, you're not going to be calculating average and standard deviation on this spreadsheet. You're just not going to be able to do it. It doesn't make any sense. You can't do it, right? Well, what if it was the same brand? Okay, well, if it was the same brand, then you just take these 3 numbers and average. And again, you do equal and you type in the word average here like we've done many times before. And you open the parentheses up and you just take your mouse and you highlight all of the data. So you allow Excel to calculate the average for you. Next up is standard deviation. So if I needed to calculate standard deviation, I do equal and I type in STDEV and I open the parentheses up and I take my mouse and I highlight the 3 data points and I hit enter. So that way it will give me the standard deviation of that number. And that's what I'm seeing here. That standard deviation to you seems awfully large, but keep in mind, these are awfully large numbers, 505, 485, 439. So the bigger the number goes, well, bigger standard deviation values doesn't necessarily mean anything bad. It just kind of goes in hand with magnitude. So for instance, if these were 5,000s and 4,000s, then my standard deviation could be in the 300s instead of the 30s. And that necessarily isn't a bad thing because standard deviation is a raw number, and that raw number is based on just a mathematical calculation. That's it. So we want to compare that standard deviation to the magnitude of the numbers that we're generating in the lab, and that's where percent RSD comes in. So for percent RSD, what happens is that to do that calculation, you're going to take the standard deviation that you're getting and you're going to divide it by the average and you multiply by 100 in order to get percentage. So this is now relative, and that's what that means. Relative standard deviation. You are looking at your standard deviation and you're putting it in relationship to the raw numbers that you're getting from the sample types. So because of that, when we do that calculation, we get 7.11% RSD, which means that normal standard here is like 10% RSD or lower. And this is an excellent job that this person did. So the standard deviation looks awfully high, but actually in the long run, when we really compare apples to apples, they've only really shown a 7% relative standard deviation, which means that their numbers are really close together based on the magnitude of those numbers. So great job for this person that did this sample type. Next up is the error. And the error, again, is going to be based on the value that is stamped on the bag if we have one. So if we do not have one, you cannot calculate an error because there's nothing to go by. We just have to report the number that we're seeing from our lab data. But if there is a number from a nutritional label and we provide that to you because we've dug and contacted the company and inquired about it and asked about it and nagged them about it until we got the number, then we need to calculate the error. So what happens here is that you're going to take your value that you're getting minus the actual that it should have been, and then we're going to divide by the actual of what it should have been, and then we multiply by 100. We do percent error here just like any other time. So I'll take my number, which in this case is 505, and we subtract what it should be, and what it should be is 250. We do that difference, and then we divide by 250, and then we multiply by 100 at the end. Here in this case, it gave them a 90% error. And that number really doesn't quite mean anything because, again, very often the lab is, or the label is going to say minimum of. It will not tell you what it should be. It will say minimum of. Now, what this opens up is that if we did not get the minimum of 250 and we got something way lower, then we possibly could go to the company and say, what are you doing? We're going to take you to court and we're going to win a lawsuit because you're selling food that doesn't have the nutritional content that you are advertising. And there is someone out there that maybe be looking at that zinc content to make sure that their animals and their pets are getting the proper amount of supplement that they need throughout the daily basis, because they only give them this hard little kernel of a cereal bowl every day for the rest of their lives. And if that was you, you would not quite like that. You would like different flavors of cereal, wouldn't you? You would like to change your diet up and not eat the same thing over and over and over all the time. You like little treats, and you like little snacks, and you like little sodas. You like to have a good time with your food. You don't eat the same thing every day. So treat your animals the same way. Make sure that they get a wide variety of different types of food, so that way they can be healthy and happy, and they don't have to worry about overly processed pet food that gets stripped down and fortified and put back together and then shipped out to you, so that way you can purchase these hard little kernels for them. All right. So with that said, keep in mind, look at these errors statements that are here. %RSD, there is a penalty assigned, and %error is not penalized if it is a reasonable number. But if it's not, then whoop, up it goes. So this is something that you want to keep in mind. Again, I can only do this, though, if you use multiple samples or replicates of the sample. If you are measuring different brands, we're not averaging. We can't do an RSD. We can't do a STDEV. We can't really compare any of those. But if I do have label content, we can calculate an error at least based on that one number that we're generating in a lab. All right, so that's the story with the spreadsheet of zinc and pet food. Nothing surprising, nothing special, nothing new that you've not seen before in another class, in another lab, but it's just this idea of a solid sample getting turned into a liquid, and then because it was a solid sample, working with this unit of milligram per kilogram. That's kind of the new little piece of nugget that's coming from this lab, and one of the reasons that we do it. All right, so with that said, good luck, folks, with your spreadsheet. Hopefully you'll get some really good data, and hopefully it will make sense. If we do find something surprising, we'll let you know. But up until this point, even the good old nasty Dollar General food that you can get for $1 for a 50-pound bag, that has actually worked out. It's not actually $1 for a 50-pound bag, but all of these brands typically have been okay up until this point. So with that said, good luck, and let me know if you got any questions. I'll see you then.